You can start, yeah.
Yeah. Right. So, good morning, everyone. Pleasure to be finally at BSides in Zagreb. I've been at many other BSides, but finally one in my home city. So, since the previous presentation was about AI, I tried to generate this image with ChatGPT-4. And the one that you're looking at wasn't generated by AI. This was a real person, a colleague of mine who generated it. Why? Because ChatGPT wasn't able to generate such an image. The prompt was literally something like generate an image which says quick and furious in the Fast and Furious theme. And every single time the car would be perfect, but it just doesn't get the words correctly. It cannot understand the words. So every single time it had a typo. And I generated about 50 pictures. Simply cannot generate this. So yeah, off to you, ChatGPT. Right, so just to quickly share some details about myself. A lot of you know me already here because I see some familiar faces. So I'm the CTO and penetration testing team lead in Figo, which is one of the biggest security companies in the region. I'm also a Sense certified instructor. I teach the web application penetration testing course, of which I'm also one of the co-authors. And as you can see, I'm addicted to Sense certificates. It helps when you can kind of go for them for free. For sure, the biggest one was the first one, GC, that is like one really, really difficult cert. So if you want to know more details, let me know. Later, I'll be here for the whole day. But before that, let me start with what's interesting for today. I'll talk about the QUIC protocol, which is something that a lot of people actually don't know many things about, but we use it every single day. Everyone here, and I guarantee that to you, use QUIC probably almost 50% of your time. Before we start with that, small quiz. Can anyone tell me 10 Vin Diesel movies? Right? Okay. The next one, Tokyo Drift, Fast and Furious, Fast 5, Fast and Furious 6, okay. Furious 7, they're getting inventive. The Fate of the Furious, all right. F9, Fast 10, wait. He actually wasn't in the second part, right? So there are only 9 Fast and Furious movies with Vin Diesel, not 10, even though there are 10 Fast and Furious movies, because he wasn't in the second part. So I just added Pitch Black, and then you can go with other ones for Vin Diesel movies. So if you go to those quizzes and they ask you for 10 Vin Diesel movies, remember there are only 9 Fast and Furious movies that he was actually in. How about 10 QUIC application protocols? Anyone knows the first one? The first one should be easy. Web? HTTP3, right? The first one is easy. Any other? How about DNS? We have DNS over QUIC. How about, I don't know, what else? How about any protocol you can think of? Because QUIC was designed as a tunneling protocol, really. So you can put anything you want on top of QUIC. Anything you want. Even though today, the majority of applications that we use are actually web applications. So I'll spend some time talking about how HTTP3 works, but you can have DNS over QUIC. You can have Samba over QUIC. And guess what? Microsoft already thought about it. It actually already works. You can have, I don't know, what else? IRC over QUIC. You can have SSH over QUIC. That's like abomination. I'll show how that actually works. All right, so a little bit of history. My idea behind this presentation was actually for everyone, when you walk outside, to understand how QUIC works on the technical level. I like details. So there will be some cryptography here. Don't be scared, nothing too difficult. what better to wake you up at 10 a.m. than a little bit of cryptography, right? But again, the goal is for everyone to understand how QUIC actually works. So a little bit of history. Everyone here, I believe, is familiar with HTTP 1.1. It has been around for many, many, many years. Actually, a lot of our browsers today will probably not use HTTP 1.1 as the default protocol. They will try using HTTP 2, because HTTP 2, which has been around for what, 9 years now, is actually used by a large number of websites today. Every single browser will, of course, support HTTP 2 and HTTP 1.1, so they can go back to HTTP 1.1 if, for example, the site doesn't support HTTP 2. Now, with HTTP 2, the main issue, perhaps for researchers, was that it brought a lot of changes. If you've ever seen HTTP 1.1, and again, I think that probably at least half of you have, you probably know that it is a plain text protocol. So you can open it in TCP dump or Wireshark, whatever, and you can read everything. It's like reading English. It's very, very simple. Sure, we have TLS to add encryption, so bad guys cannot read it. But behind TLS, it is still a plain text protocol. There is nothing very special about it. With HTTP 2, they completely changed the things. It is a binary protocol. So with HTTP protocols, there are actually two things that we are interested in: the semantics and the syntax of the protocol. The semantics tells us that the protocol remains the same on the high-level methods. So with HTTP 1.1, we have what? Get, post, put, and so on. With HTTP 2, you still have the same methods. So the requests look the same, but they change the syntax of how this is mapped onto the wire. So in HTTP 1.1, it's just directly translated, plain text. With HTTP 2, you have a binary protocol. It's compressed, everything is in frames, and even though it looks the same for us on the high level, on the wire, it's completely different. It's multiplexed, not pipelined. What does it mean? With HTTP 1.1, you send one request, you wait for it to finish. The next one, the next one. With HTTP 2, you send multiple requests, they split everything into frames, and you start getting all the frames back at the same time. Google says it helps with speeding up things, and if Google says so, who am I to complain? They also solve one problem that HTTP 1.1 had, and this is called HOL, head of line blocking. So with head of line blocking, and everyone here experienced that, you open a website, there is a small JavaScript file, which is 2 kilobytes, and there is a backend image, which is 50 megabytes. And then you wait, right? For that image to load, nothing works. Image loads, now you download 2 kilobytes of JavaScript and everything starts working immediately. This is called head of line blocking, right? So HTTP 1.1 has that built-in, let's call it feature, but it's actually a weakness. So with HTTP 2, we have streams, we have frames, so we can send both the 50 megabyte picture and the 2 kilobyte JavaScript at the same time. So they will be just, spread, and we'll get those 2 kilobytes JavaScript much, much, much quicker. So hopefully our web application will start working faster. So this is what it looks like on the wire. With HTTP 1.1, you usually have 6 connections that your browser will open to the target web server, and it will use them in parallel to fetch data, right? 4 or 6, depending on the configuration of your browser. Now, when you are Google or Facebook, and you have every single server in the world, browser in the world, that opens 6 connections to you, that's not nice, right? So in order to handle 1 million users, you need to handle 6 million simultaneous connections. That's how browsers will work. With HTTP 2, we only get 1. There's only 1 connection, and we get data in frames over that 1 connection. Ooh, so much nicer. No wonder that it was Google who actually invented QUIC, because they wanted to make things not only faster, but perhaps a little bit better for their servers as well. So with HTTP 2, over the wire, we have binary content, goes over 1 TCP connection. We have TLS to ensure confidentiality of data, and then you have HTTP 2 requests. If any of you here are doing pen tests, and you, for example, need to test a web application, and you send your web application through burp or ZAP, whatever interception proxy you use, understands HTTP2, and it will actually show the request to you as if they are plain text, but it actually parses binary data, right? They're not plain text anymore, but we still see them in burp as plain text, so we can proceed with our tests. So why did they invent HTTP3? Well, HTTP2 solved a lot of things, and as I said, one TCP connection for per browser to a server, that's actually great. So we solved HTTP head-of-line blocking, right? We don't have pipelining anymore. So I get that big 50 megabyte picture and 2 kilobyte JavaScript back at the same time. So I solved the HTTP head-of-line blocking. I still have TCP head-of-line blocking. What if my packets get lost, right? So I don't get new packets back. Now everything is slow. We need TCP to, again, start acknowledging packets, you know, the retransmission and everything else. So Google's engineers were actually looking at this, and they were thinking about how to improve speed of TCP. Because when TCP was originally invented many years ago, our networks were not so reliable. So we had a lot of packet loss. We had a lot of slow networks. Today, especially like with new kids, if it's not, you know, 5G, they don't even connect to that network, right? Too slow for me. So today, we perhaps do not need to worry that much about packet loss. There are other things that we want to speed up. But how do you change TCP? You don't. There are a zillion devices around the world. You cannot change TCP. There are small tuning things you can change, and these are called TCP flavors. They tell you how to deal with packet retransmission and stuff like that. But it's only so much you can do with this. Only some minor tweaking and fine-tuning. And then Google said, wait, there's another protocol that doesn't care about connections. We can throw packets around as much as we want. We can do with them whatever we want, and it's called UDP. So why don't we build everything on top of UDP? So with QUIC, what they've done is actually build TCP on top of UDP, then add a little bit of encryption over there, and some extra spices in this particular protocol. The full publication was in 2021 as RFC 9000, but it has been around so much, as you will see in a couple of minutes, that it feels like, you know, it was introduced 10 years ago. So the one thing to know at this point in time is that HTTP3 is actually just HTTP2 that is put on top of the QUIC protocol, right? So from the HTTP point of view, we just take HTTP2. Nothing has changed. But we have the underlying transport protocol that is different. And this is, of course, QUIC. Among other things that they improved, and I'll tell you one other that you'll probably agree with me that it's quite cool. On the left side, you can see, for example, HTTP2 connection. We have TCP, and then we have TLS 1.3 on top of it. And this is what the handshake looks like. Like we have the SYN, ACK packets, everyone knows about that, the TCP handshake. Then we have the TLS handshake. So we send the client hello, we get back server certificate, we get some messages, and then finally we can issue a GET request. Google wanted to decrease the time it takes for a browser to get some data back. So they don't have all of these steps anymore because obviously they use UDP. So they actually, in the very first packet that's being sent by your browser, every single browser over here, contains some connection information as well as TLS hello data. This allows the server to immediately send something back in the second packet. And basically, in the third packet, we can already send a request. So we decreased the number of packets over there. Ooh, right? Talk about speeding up things for, I don't know, 5 milliseconds maybe. Well, for servers, this means a lot, not for users. There are a couple of other cool things for users. And one I really like, that one is not fully operational yet because it's still in draft. But the idea about using QUIC and UDP for connections is that you can now have the following. Let's say that you woke up in the morning and you started streaming something on YouTube or, I don't know, SoundCloud or whatever you like the most. Let's say it's YouTube. And you're streaming at your home and your phone is connected to your Wi-Fi network. What happens when you exit the home? your phone connects to whatever 4G, 5G network it is, and you lose your stream, right? Everyone sees this for a little while, and then you start getting data again. Why does this happen? Because we changed our IP address, right? And the TCP connection that we had to YouTube simply died. Our IP address is now a completely new IP address, had nothing to do with the previous one. We need to establish new IP connection, TCP IP connection to YouTube, and this takes a little bit of time. So if our browser perhaps buffered enough data, this might happen in the background and you won't see it. If it didn't, then you'll see, something that new generations don't like to see, right? So with UDP, we can actually move IP addresses without any data loss, because there are no TCP connection session handling here. Session handling actually happens in UDP packets, and with UDP packets, we don't care about IP addresses. So you switch from one network to the other, and the stream of data continues without any packet loss. Quite cool, right? We just move around the networks. And that was one of the ideas. That was one of the ideas because today, when we use our mobile devices more and more, we might be switching mobile operators. We might be switching cell towers, whatever. So we might change our IP addresses constantly. So that was one of the ideas behind QUIC. As I said, it's absolutely everywhere. Anyone here that uses YouTube? Is there anyone here that doesn't use YouTube? Okay, thought so. By default, YouTube uses HTTP3 or QUIC. If you use Chrome or Firefox or even Safari, right? Apple is always the last one to support new things. If you use any of these browsers, they will automatically use QUIC or HTTP3 to fetch data from YouTube. If you want to see what it looks like, open the Developer Tools console in your browser, go to the Network tab. This is what I have in the slide, but you will need to add, this might even work. You will need to add the protocol column, so you need to right-click and add protocol, and then you will see which protocol is being used. When it says H3, it means that you are using QUIC or HTTP3, right? So Google uses that, any Google services, YouTube, Facebook uses this, Uber, your application, mobile application on Uber, it uses QUIC because it allows it to change IP addresses quickly, right? And they want to have those updates as real time as possible. Instagram, Facebook, a lot of big providers use use QUIC today. Now, if you wonder how it works behind the hood, and that's what the next section will be about, is that, as I said today, browsers still try to use HTTP 1.1 and HTTP 2 by default. So in the first request, very first request that your browser sends to Google, in the response, in the HTTP response headers, there will be a new header called alt service, alt SVC, that tells your browser, hey, even though you sent this over HTTP 2, by the way, I support HTTP 3. And over here, we can see that two HTTP 3 protocols are supported. The RFC one, RFC 9000, and this is HTTP 3 draft 29, something that Google invented, so it supports two versions of the HTTP 3 protocol based on QUIC. And we can cache this for 30 days. Again, what does this mean? Next time you go to YouTube, your browser tries to use QUIC immediately. By the way, just in case you're wondering, if you stream YouTube in your company at work, if they allow you to do that, right? If you go through proxy, your browsers will automatically fall back to HTTP 2 because they know that proxies generally today do not support QUIC. So this will happen when you're at home. There are no proxies. Or if at work, there are no proxies you go through, and UDP on port 443 is allowed. Of course, if there is a firewall blocking that, it will not happen. Right, enough about introduction. Let's do a deep dive. See the advisory at the bottom. Some crypto is about to be shown, so just prepare yourself, but I'll make sure that everyone understands. You don't need to be a crypto expert. I'm not a crypto expert, but let's see how this works. So when I started preparing for this presentation, I actually wanted to do some research about QUIC. I was like, okay, let me download the RFC. I'm going to read the RFC. I'll be an expert. I might even find some interesting things. So let me do that. So I downloaded the RFC, converted it into PDF, and it had 151 pages. So I was like, right, not going to happen. just way too much. It's actually a quite complex protocol. And they added so many insane things in the protocol, as you will see. Like, I have no idea why they added it, and you probably will agree with me, I hope. But hey, it works, right? So let's see what happens behind the hood here. So first of all, again, one of the ideas behind QUIC was to, as they call it, make security and privacy a first-class citizen. What does this mean? This means that QUIC encrypts everything. Absolutely everything, as much as possible, from the very first moment that QUIC can encrypt something, it actually will. HTTP2 can be sent without encryption. It supports modes without encryption. It's still binary, it's compressed, right? So you need a parser to read it, but there's no encryption. QUIC actually doesn't even support any modes that don't include encryption. It must be encrypted, absolutely everything. They will also try to encrypt metadata as much as possible. So yeah, if any of you are doing offensive things and you stumble upon, I don't know, Darktrace or Recta or ExtraHop, well, these devices will start having more and more problems analyzing passively analyzing network traffic because everything is encrypted. It also relies on TLS version 1.3, the very latest one. Again, this helps with shorter handshake because that was included in TLS 1.3. So QUIC actually relies on that. Another thing that makes it a little bit more difficult for passive devices to analyze QUIC data is that QUIC almost exclusively uses elliptic curve cryptography, EC cryptography, which means, and this is called perfect forward secrecy, which means that unless you actually have the keys from the devices that are talking between themselves, if you get the keys from the server, you won't be able to decrypt the data. It's elliptic curve, so these two endpoints that talk to each other, they will use Diffie-Hellman to come up with a key for encryption. So forget about passive analysis. The only way to correctly analyze QUIC is to have a man-in-the-middle device. Passively, game over. You'll only be able to see certain metadata that I'll show in a second, and that's about it. Even with secret keys from the server, you won't be able to passively analyze anything. So these settings are sent in extension-supported groups. There are 3 curves that are being used. You can see them here. The X25519 is the most commonly used one. This is, again, what our browsers use by default. So when you go and connect to YouTube, the very first step your Chrome or Firefox browser will do is to create a public-private key pair that is based on elliptic curve cryptography. We don't need to know other details, so don't worry. It won't get much worse than this. Now comes the fun, right? You need to talk to someone for the very first time in your life. You can't start using encryption in very first packet. Well, you can do certain things, as we will see, but you can't immediately encrypt everything so no one else can see it, because we still haven't exchanged any secrets. We need to do that somehow. So this is what QUIC does. And this is version 1. Version 2 has been released as well. It's basically almost the same. They just change a couple of things. But as far as I've seen, almost no servers support QUIC version 2 yet. Now, here is the funny thing. We'll need some kind of a salt. And the initial salt in QUIC is always this number here that you can use. See? And this is actually the first SHA-1 collision that was found by Google researchers. A little bit of history over here for fun, right? This is always the initial salt in every single browser, in every single QUIC connection. Now, QUIC uses 2 algorithms that you might not have heard about. Indeed, for me, this was something like, okay, let's see what this is. These are HMAC key derivation functions. Something like PBKDF2, if you know about PBKDF, or bcrypt, if you are a developer. So with HKDF, there are 2 functions, extract and expand. The extract function takes certain data, something like a salt and a secret key, and produces certain crypto material. And then we take whatever we get back from extract and we push that into expand, So we get the created crypto material, some information and some other things to get some other crypto material. Make sense so far? Okay, everyone nodding? Yeah. We don't need to know more than this. If you want to see how HKDF works, yeah, just check, but we don't need to know more. Now, every single client in the world that uses QUIC will perform these operations. These are all based on two things. The salt, which is always the same, and a randomly generated bunch of bytes over there. These randomly generated bytes are our public key, right? So remember I said here that we will create a public-private key pair. So we'll do the following. Take the salt, take the public key, and then calculate all of this. And we will use these other keys for encryption. But now the problem is, how do you tell the other side what you're going to use? So there is a catch-22 here that obviously they couldn't solve, and they went through some crazy things, as you will see in a minute. So as I said, QUIC tries to encrypt absolutely everything. And this here is a very first QUIC packet in a connection that I created to another server that supports QUIC. And as you can see, you don't see anything. You only see a couple of headers, like the version, which is 1, QUIC version 1. We see some destination connection ID, and everything else is encrypted. I was like, how does this work? How can the server know how to decrypt this data, right? It's a very first packet. The server has no idea who we are. Well, actually, see here, in order to calculate everything at the bottom of this slide, you just need two input ingredients. The initial salt, which is always the same, and random bytes, which is our public key. Public key, everyone can see it, right? This here is the public key. So the destination connection ID. So the client sends that information to the server in the very first packet. And now my question to everyone here is, if you're sniffing this traffic, you see the destination connection ID, which is the public part of the key, and you know that the initial salt is always this. Can you decrypt the packet? No, why not? Check this. You know the salt, you have the initial random. Can you run the same calculation? Why not, right? So this is one thing that I thought is a little bit insane. Why? Because they added some encryption here that anyone in the world who's sniffing packets can decrypt. That will only allow you to read metadata, but why go through all the trouble to encrypt it when everyone who sniffs the traffic can decrypt it? Okay, one insane thing. Not the most insane they did. The next one is the most insane they did. In order to make things a little bit more difficult, they decided to additionally encrypt two more pieces of data from the header. Let me just go to the previous slide. They wanted to encrypt the packet, the packet version, this initial part, and the packet number, which here is 0, because it's the very first packet in a connection. So someone in Google decided, hey, why don't we encrypt these two additional bytes in the packet header? And in order to encrypt that, we will do the following. We will take a 16 bytes payload, which is already in the packet. We'll slide it 4 bytes, just for fun, because we can. Why not 6? Why not 5? I don't know, they slide for 4. Then they take these 16 bytes. They use the key, which is generated from the first calculation that I had 2 slides ago. They create a new encryption key, and they just encrypt these 2 bytes with that key. Why would they do that? Every single server in the world now has to decrypt this, right? And anyone in the world can decrypt this. You didn't achieve anything against attackers. I have no idea why they did this. Now, of course, people started adding support for that very, very quickly. And as you will see in the next slide, we can actually decrypt the data because we have all the ingredients in the packet itself. So to go back, this defines how to encrypt just 2 bytes, right? The rest of the packet, the payload at the bottom, is encrypted. Again, I'll go back 1 slide with these 2 keys at the very bottom of this slide. But if you have the salt if you have the random value, which you can see in the packet, it's plain text, that's the destination connection ID, you can calculate all of this and you can decrypt the rest of the packet. Make sense so far? Okay, this is the crypto level we'll go through. So after this, it gets easier, trust me. Right, so we need the client key, we need the client initialization vector, we have that as we can calculate that. We need the record number, which is 0. We need those two keys, we know the initial salt. We need the GCM authentication tag because they use AES encryption with GCM for authentication. This will be the last 16 bytes of the packet, always. And we need additional authenticated data. This is kind of cool. Additional authenticated data is the whole header. This prevents someone from modifying something even in the plain text parts of the header because they would need to calculate everything again. Right. So if you ever need, this is the CyberChef recipe. Quite simple, actually. You just use AES decrypt. You need to put proper values. You calculate the key and the initialization vector based on the formulas I had on the previous slide. Put the mode to GCM. Just add the tag and additional authenticated data, and you basically decrypt the packet. And really wise researchers did this on our behalf. So if you use the latest version of Wireshark, it will actually do this automatically, right? All the data is there. Why not? There's nothing preventing you from decrypting this. So once you open a PCAP file in Wireshark, you'll actually see the initial QUIC packets decrypted, right? But only metadata headers. After this comes TLS 1.3. There is no decryption there, unless you have client keys, right? But if you have only the server key, no decryption. Remember, it's perfect forward secrecy. We can't decrypt that. It comes after this. So in the crypto QUIC frame, and again, QUIC has frames similar to HTTP2, we'll see a bunch of interesting things. For example, here we have TLS 1.3 record layer, and we have a bunch of extensions over here. By the way, if you take a look at this, it says version TLS 1.2, which it is not. Does anyone know why? Did anyone dive so deeply into network protocols to know why it's TLS 1.2?
I think it's some backward compatibility with, it's actually TLS 1.3, but it's like lying.
Very good, Jad. I knew he might know. Right, so when they released TLS 1.3, there was a lot of firewalls, whatever, reverse proxies that only understood 1.2. So they decided not to create a new protocol version. So it kind of puts TLS 1.2, and then everything else you need for exchange of keys and stuff like that is in the extension headers, right? So it will always say TLS 1.2, even though it's actually TLS 1.3. And you can see here the Cyper suites which are supported and so on and so on. This is the standard TLS 1.3 handshake, nothing that specific about it. There are two interesting things here that I kind of would like to spend a little bit of time on. The first extension is the application layer protocol negotiation, ALPN. This is what allows us to put any protocol on top of QUIC. As long as the client and server know how to talk about these protocols, you can put whatever you want over here. So in this example, we have the protocol which is H3 or HTTP3. You can put here whatever you want. You can put IRC, you can put Samba, you can put anything you want, as long as the server knows how to talk about it. At the bottom, you can see QUIC transport parameters. And again, we can see a bunch of parameters here. This is how the client and the server negotiate about the number of streams, the number of frames, their timeout and stuff like that. So these are, again, some things that can be tweaked a little bit to make it faster or slower, depending on what your requirements are. Now, with QUIC, every connection that you make to a server will have its own ID. And that is how QUIC actually knows who you are. The QUIC server. QUIC server doesn't care about your IP address. It's UDP, remember. We can change IP addresses as much as we want. So it uses connection IDs to identify us. Let's go back to see it. Where is it? Here. See? The destination connection ID, length, and the value. This was our public key. And now in the response packet that I don't have shown here, you would see another field. It's over there actually. Source ID connection, but it's not sent. This is what the server sends back to us and says, okay, this is your connection ID. That's how I know who you are. So if you change IP addresses, I don't care. When you send the data back to me, the destination connection ID and the source connection ID define our pair, right? So we can just migrate around the world as much as we want. We don't care about IP addresses anymore, which is really, really, really cool. Besides allowing us to migrate IP addresses, there is one other crazy benefit here: 0 round trip time, which means that if you connect to YouTube today, and now you go somewhere else, and you start your laptop again, and you send a request to YouTube, your browser probably cached the connection ID values. And this allows your browser to immediately send a packet which is encrypted, because we already exchanged all the crypto material we needed to, and send the request in the very first packet. 0 round trip time. You send the request immediately. See why Google likes that, right? They decrease on processing time on the servers. They make everything faster for their users. I mean, 10 milliseconds faster, so we don't notice that, but anyway, someone is happy over there. So this is kind of really, really crazy. And we can even have multiple streams of one connection ID. So it gets very, very complex if you go to that level of the protocol. Finally, to spice things up, well, anyone can introduce new QUIC protocols. Remember, first of all, we have application protocols. They live on top of QUIC. That's the ALPN, application layer protocol negotiation. But even for QUIC, you can create your own QUIC protocol. You can change certain things. You can't change the protocol completely, but you can modify certain things as we have TCP flavors. So guess what? Who would want their own protocol? Google, of course, because they were the original creators. So they have own QUIC protocols. Then Facebook said, you know what? We're going to do it better. And they named their MVFST, which they say it's called Move Fast, kind of cool. So that is Facebook's version of the QUIC protocol. They open source it, so you can actually get the implementation. Mozilla created their own. Microsoft said, you know, Microsoft always has their own, right? So they created their own. And if you deal with some Chinese attackers, then you can see Tencent using their own QUIC protocol as well at the bottom. They all have their IDs. Only some have been officially registered, right? Some of these, they simply use it. As long as the client supports it, that's it. And remember, they can even advertise it. Remember that header that I had, alt service? You can actually support multiple QUIC protocols. So it is up to the client to decide what to use. Or you might decide not to advertise it, have it running as a backdoor, and then when someone connects with a very specific version of the QUIC protocol, you actually execute something. It's perfect for backdoors, as you will see in one other example. So what applications do we have here? The first one we already talked about, the obvious candidate, HTTP3, something that, as I said, we use all the time. Again, not too difficult. It's HTTP2 on top of TLS, on top of QUIC. Bootstrap is with that response header. And by the way, if you ever want to, for example, prevent applications from switching to QUIC, and you have a man in the middle against an application, perhaps with a burp proxy or something else, you just intercept the response and you delete the header. So when you let that pass through to the client, your browser will think, oh, the server doesn't support HTTP3 because there is no alt SVC response header. And the server will think, oh, the client didn't switch to QUIC, so it doesn't support QUIC, so we're going to remain talking HTTP1 or HTTP2, whatever they do. So we can kind of go around because our tools still do not support QUIC. Burp doesn't support QUIC, ZEP doesn't support QUIC, so we can't use those tools to perform tests. Before I go into some other things, just one cool, again, a little bit crazy, but cool feature that HTTP2 already actually has that a lot of people don't know about, and it's called the push promise. So what is the push promise? It means that the server starts sending web responses back to you even before you asked for them. It's like, how do they do that? So it's actually quite simple. You open, I don't know, Srce.hr, right? And you go to the top level URL, and your browser will send a request, which will be what? Get/HTTP to host Srce.hr. Now, you usually get back what? Index dot whatever it is, the contents of the top level page. But now the server knows that if the index.php or whatever it is, doesn't matter, contains a bunch of images, the server knows that your browser will actually send requests for those images immediately after it gets back the index page, right? In order to render the web page. Make sense? Yeah. So it starts sending those immediately back without you even asking for them. So do something like get/, and the server says, here is your index.php, and by the way, here is one image, here is another image, here is another image, because I know you're going to ask for them. Again, Google liked that, so they can push data more to people. So even though you didn't ask for these images, you actually get them in the response back. Now, what else do we have here? DNS over QUIC, or called DOQ. This actually became a standard in 2022. I don't see this used a lot. Actually, even the big DNS providers like, I don't know, Cloudflare, Google, I think they don't support DNS over QUIC. They do support DNS over HTTP. And you probably already have that in your browsers, because browsers do support it. You know, when they send requests over HTTP to 1.1.1.1 or something like that. They don't support DNS over QUIC yet. I think they will start adding support for this. So don't mix this with DNS over HTTP, right? This is actually the DNS protocol built on top of QUIC. It's not using HTTP. DNS over HTTP can be over QUIC as well, but then you have QUIC, HTTP, DNS. Here we have QUIC, DNS. It's immediately on top of DNS. If you're looking at network traffic, by default, it should be using port 853. How about the next one? And this is the one that actually got me into creating this presentation in the first case, because I started playing with creating command and control channels and backdoors over the Samba protocol. And then I saw that Microsoft happily announced that they will start supporting Samba over QUIC. So your Windows file shares over QUIC. Today, they work over TCP. Anyone knows the port? 445? 5 for Samba, right? So with QUIC, they actually move it to 443 because it's over UDP, right? And initially, again, they only had this working in Windows Server 2022 Data Center Azure Edition, so only were able to have it in cloud. But guess what? About 2 months ago, Windows Server 2025 started supporting Samba over QUIC. So imagine this. Someone hacks your server, and they actually enable this in the background. And now, if they can use UDP on port 443 to talk to your server, they can actually connect as a Samba share. And Windows 11 clients already support that. So it's kind of crazy. So with these new versions, they will still use TCP by default. They can switch to QUIC. And Microsoft decided to call this SMB VPN, Samba VPN. And you will see them advertising this feature as something like, you need your users to access your file shares. You don't need VPN anymore. Just open UDP port 443 on the internet, and they can actually connect directly to your Samba shares over internet. What can go bad there, right? And everybody else. Well, they use certificates, and you have still authentication over there, of course, right? Yeah, you can trust Microsoft. I mean, but you can literally open 443 on the internet and have your Windows 11 clients connect over the net and access Samba shares, and your users will see them as normal mapped drives. They actually have no idea which protocol is being used in the backend. Again, what can go there? For final abomination, SSH3. Has anyone heard about SSH3? Okay, there's one. So who is using SSH2? I'm not saying one, everyone, right? He is using SSH2 for something. Well, some people decided to create a new version of the protocol. And when I saw that they are migrating SSH3 over QUIC, I was like, no, don't do that. But actually, when I installed it, it's not that bad. I kind of liked it, to be honest. So what they did is the following. They took the SSH protocol and they put it, check this, on top of HTTP3. And then they used QUIC. So what do you have here? You have QUIC, you have TLS, you have HTTP3, and then you have SSH. So you have like a layer, stack of protocols. It works amazingly well, right? It really works well. They say it's not production ready yet, but you can try to use it. There is a server in the client. You know why I like this? There was one occasion when I was playing with, again, some backdoors. And when you install this server, it will appear as a web server, even though you have SSH over that. If you scan it, it looks as an HTTP3 web server because it uses HTTP3 web, right? I mean, it's perfectly fine. But they already support, you know, tunneling and stuff like that. So quite scary. So as I said, sorry? For reverse shells, it's perfect for reverse shells. That will look as web traffic, right? I mean, you can always have that, it's kind of a shell, but here you actually have SSH protocol over web. Right. So just to finish, almost on time, I decided to check who is using QUIC, right? Let's see if you can find some servers using QUIC. So my favorite scanning tool is Nmap, as some people here probably know. And I started scanning various IP addresses with Nmap. And then I was a little bit sad because I saw that Nmap kind of failed miserably. Why? Because QUIC is a UDP service. So first of all, scanning UDP services is not simple, right? You can't just send a packet and get something back. You need to send a correct packet to get something back. Otherwise, you don't know if the service doesn't exist, if the packet was lost, or you just sent something incorrect over there. So scanning UDP services was never simple, right? When someone asked me in a pen test, how about you scan Class B network for UDP? How long does it take you? 1 month. What? I need to send all the packets again, right? To see what's going on. So this is the very latest version of Nmap. And as you can see here, I scanned YouTube on port 443 on UDP. I even added version all. This tells Nmap to take every single probe from the Nmap services probe file, and it failed. It found that it's open, but doesn't know what's there. Right? So it failed in fingerprinting the service, actually. So I started, you know, going around the internet to see what we can do here. And there were a couple of researchers that started working on QUIC. And they were really nice because they forked the ZMap scanner, which some of you might have heard about. And they actually added a module that allows us to scan QUIC services because that module knows how to speak QUIC. So it is much better. So you can actually download it. You can scan various networks with it, but just keep one thing in mind here. The RFC 9000 description of the QUIC protocol requires that every single QUIC packet is padded to 1200 bytes. Packets are always 1200 bytes. They do that so they prevent some, you know, analysis of network traffic. Am I sending just one character or something big? It's always, packets are always 1200 bytes. So when you scan large networks, you'll be throwing a lot of data at them. It's not just SYN packets for TCP services. Here, every single packet will be 1200 bytes. So I decided to scan Croatia. Thank you, Mislav, for the nice one-liner to pull up the Croatian IP address space. So I scanned Croatia. It's about 2 million IP addresses. Yeah. Times 1200. Okay, we have fast networks today, right? I found 230 IP addresses in Croatia that actually are using the QUIC protocol. And you can see who uses them over here. So 59 are used by Google. These are local Google points of presence. 38 by Facebook, 4 by WhatsApp, 120 by Akamai. Then there were 2 very weird traffic devices. I didn't want to pick there, but these are some devices that support QUIC. And then see the last one? I was like, seriously? This is, all of you who are local here, you know which faculty this is. And I was like, seriously? Like no one else is using QUIC, but this particular server, someone is very advanced over there. But actually, no, It's just a host name that points to the plus hosting that are actually supporting QUIC on their server. So it's one hoster that supports QUIC, which is kind of cool. So what else do we have here? ZMap only allows you to identify services which support QUIC. It will not collect any additional data. And I wanted to get more information about, certificates. Can I get anything else about those services? So again, the same authors produced another tool called QScanner, which is written in Go. It's quite fast. It's a bit tricky to compile it, but it's not too bad. And this tool takes the CSV file from ZMap, and then it can scan all the results and pull out certificates, supported protocols, and stuff like this. It only supports HTTP3 though. So you can't use any of these tools to scan, for example, for Samba on QUIC or DNS over QUIC or something like that. So what we did, a colleague of mine, Fran, who works with me, created a scanner, a new QUIC scanner that, there you go, will be released today on GitHub. Relatively simple tool written in Python. So if you want to scan 4 billion IP addresses, good luck because it's Python. But it's not too bad either. It's relatively fast, relatively quick, pun intended, right? And this tool will allow you not only to identify QUIC services, but it will also brute force all the registered application layer protocol negotiation IDs. So it will allow you to identify whether there is something else apart from web sitting over there. We plan to add a few more features over there. I know that some things are missing, but it's actually quite nice. We tested it a lot. It's relatively fast because he added multi-threading, so it starts with 50 threads, and you can actually scan other ports than 443. You can do whatever you want with that. So here, I'm just using the tool to scan YouTube and 11111 and Facebook on ports 80 and 443, and then you get back the results port. You can see the server versions. This is the version of the QUIC protocol that is supported, and you can see Facebook supports all of their weird versions of the protocol that always start with face. I mean, it's kind of cool. Yeah, Microsoft picked ABCD. Boring. Facebook picked face B, and then they just add the number over there. So for the last thing, and we'll be just good with time, how about using QUIC for port knocking? So port knocking is a very old method of actually starting backdoors that you have planted perhaps a long time ago. So what was originally port knocking? You had a service which was maybe listening on UDP port 10,000, and there was another backdoor that wasn't started. So you actually needed, or the attacker wanted to send a packet to port 10,000. They knew exactly what needs to be in the packet, and then the backdoor started. That's called port knocking, right? The backdoor is not active until I knock on the port. Well, we can use that with QUIC very, very easily, and it's actually amazing. Why? Because we can implement our own application layer protocol negotiation extension that only we know about. Here, I called it Infigo, just for fun, right? And until you send a QUIC packet that contains this exact ALPN, nothing happens. It looks like a perfectly legitimate web server. But once it sees this one, it can establish a QUIC connection with this particular ALPN. Of course, if you are sniffing traffic, you could see that the protocol is a little bit weird. So I could, for example, use something like I don't know, IRC or Samba or whatever else. So at the end, I hope that everyone here managed to understand how QUIC works. I think that in next year or two, we'll still see what can be done and how QUIC can be abused. I'm quite sure that there will be some very, very cool things about abusing QUIC. And definitely if you are on the defender or offensive side in your company, if you're offensive, then it's worthwhile checking what you can do with this. If you're a defender, something to keep an eye on. Today, I think there is only one firewall vendor that I will not name that supports QUIC man-in-the-middle inspection. If you go to some other really well-known firewall vendors, they will actually in the documentation tell you disable, block UDP port 443 because we cannot inspect it, right? They still haven't added inspection because remember I said passive analysis, game over, right? We need to have man in the middle to see what's going on here. So if you are a defender, something definitely to keep an eye on because who knows when, if not already, some attackers are using QUIC. So I guess that's it for me. I hope this was interesting.
For this detailed presentation. Any hands, questions?
More crypto? No?
More crypto?
Sorry,
Yes.
Yeah, wait.
And how basically QUIC, when using, let's say, standard HTTP 3, is dealing with denial of service attacks and so on? Because you know, in standard protocol you have a TCP, and over there is the upper layer who is responsible to manage DNS, denial of service and so on.
Great question. Let me just go back to one slide here. Actually, I wanted to add that, but I thought that I won't have enough time, but it's a great question. So see these parameters over here. If you remember, this is the very first packet that I decrypted because I have those secrets in the plain text. So I can see the metadata. These parameters over here, like initial maximum stream number, data, stuff like that, these are something like TCP acknowledgement numbers and windows. And with this, a server can tell the client, you know, how much data it wants to receive. It can kind of shorten that window. It can drop certain things. So this allows them to kind of handle, to a certain extent, denial of service attacks. But your question is great. For anyone else who wants to perhaps see a little bit more, there were some attacks already because this is not perfect. And people actually found a way on even, you know, reflecting some traffic because it's UDP. You can spoof packets easily. So denial of service might be a bit bigger problem here. So the packet is 1200 bytes, 1200 bytes. It's always like that, right? And if you can do some reflection, depending on your send, you can easily get denial of service or reflected denial of service attacks. So there were some published already. They fixed some, right? But there are still some things that are not handled perfectly. Good question, thanks.
Any more else? No? Thank you, Bojan.
Thank you.